Morning, nerds. Today, we are going to start focusing on the algebra of logarithms, and our video features artwork from our very own Miss Hannah Whitfield. Nothing? Nobody? Round of applause? Anything? There it is. Yes, yes, yes. I guess that's me as a Muppet. Yeah. And yes, ew, really, Ahmed? Guys, slob. Anyway, I love logs. That's true. And the Gators. That's true. I bleed orange and blue. Okay. Yeah, well, you know, haters gonna hate. Anyway, exponential, logarithmic equations, and then the big boys, the inequalities, which are very special. Logarithmic inequalities do some weird things. I'm not even going to bother reading all this or any of this one-to-one property stuff. We've laid the groundwork for all of that stuff, okay? We've laid the groundwork for immediately jumping to solving exponential and logarithmic equations. We've already done all the hard work. The hard work was understanding what a logarithm is and why it works and things like that. Knowing that exponential functions and logarithmic functions are inverses of one another as long as they have the same base. And we can use that concept to solve both algebraic and, exponential and logarithmic equations. My phone is blowing up. We're just going to... No, it's one person. I only have one friend. Okay, let's go to it. We're trying to isolate x. That means we have to use SAD-MEP. Okay? X happens to be in an exponent position, but that's one of the last things that we're going to try to get to. Instead, first we have to deal with the 24. So we're going to need to divide both sides by 24. I'm sorry? Okay, anyway, that gets us 1/2 to the x over 3 equals... And you know, 6 over 24 reduces to 1 over 4. Now the idea is, if you can, get both sides to be the same exponential base. And this is one of those times that it is possible. Because 1/2 and 1/4 are both powers of 2. And what's even cooler is, since they're both fractions, we could actually say that 1/4 is a power of 1/2. If you're uncomfortable with that, then say this is 2 to the negative 1, this is 2 to the negative 2. But we don't need to do that. We could write it like this. And we now have an exponential equation where both sides are exponential base 1/2. Equal sign says everything on the left is exactly the same as everything on the right. And when you're in Algebra 1, you learn how to solve things, exponential equations like this. And in Algebra 1, what they tell you is, hey, since the bases are equal, all we have to do is set the exponents equal and solve for x, right? But that's not algebra. Where did the 1/2s go? So what we tell you in Algebra 1 is, well, we don't need to worry about them because they're already equal. But we now know enough to legitimately say where the 1/2 went. We canceled them with logarithms. So at this point, you would use log base 1/2 of both sides. And since both sides are exponential base 1/2, the log base 1/2 and exponential base 1/2 cancel each other out. The result is still the same, that x over 3 equals 2. But the algebra of where did the base go is the logarithms canceled it. That's why we like the exponential bases to match. Multiply both sides by 3, and you get x equals 6, and that question is finished. But you've been solving exponential equations for a long time. Like I said, you should have done them in Algebra 1. I know you did them in Algebra 2. This is not our first rodeo with them either, I don't think. We've solved exponential equations in here before, right? Exponential equations? I can't remember. I'm going to be honest with you. I teach 3 different math classes, and I just finished up logarithms with my IB kids. I'm in the middle of logarithms with you guys, and I just finished exponentials with my Algebra 2 kids. So like all of my knowledge gets crisscrossy. Did we use the calculator to solve? Okay, so this is technically the first time we've seen it, at least this year. Okay, great. Here. Yay, Loisimos, we did it. These have logarithms in them. Lucky for us, they both say log base 3. That means we're going to be able to cancel them. But not yet. You cannot ever cancel a structure until it's alone in mathematics, which is why I had to isolate this exponential base before I could cancel it. Same thing is going to be true for these logarithms. We cannot cancel a logarithm until it is isolated. That means that 2 can't be there and that 3 can't be there. Ahmed? The coefficients can be condensed back into exponents of the argument using a logarithm condensing rule. That leaves us with log base 3 of x squared equals log base 3 of 4 cubed. Because both sides are log base 3 isolated, we can cancel them with exponential base 3 on both sides. So with exponential base 3 on both sides, where we treat the purple stuff as exponents of a base 3, allows us to do this, leaving us with x squared equals, and 4 to the third power is 64. There we go. We cancel this square with a square root. It's almost like nobody's realized that I didn't write the answer yet. I need you, no, nothing is messed up yet. I need you to tell me what typically happens when you cancel a square with a square root. Plus or minus typically occurs. Wait, please. Yes, typically you would have a plus or minus. And are there occasions when you would have the plus or minus? Yes. So I'm going to write the plus or minus, and then I'm going to remind you of some terminology that we haven't used in a while. What's the word I'm looking for? All of a sudden my mind just went blank. Extraneous solutions. Because logarithms have restricted domains, it is possible to get extraneous solutions the moment you eliminate the logarithms. It's just like when we were solving square root equations. Remember, square roots have restricted domains. So the moment you remove the restrictive symbol, you have allowed the possibility of extraneous solutions. And technically, you should all have said plus or minus 8. Nobody said plus or minus 8. However, the argument of a logarithm cannot be negative. So negative 8 is an extraneous solution. So the only true answer is positive 8. But the reason why we needed to talk about the plus or minus is because sometimes you would get 2 answers. It just depends. Mr. M, what are you talking about? Well, let me show you. If the original question had said this, if that was the original setup and not this, if this was the original equation, then it does have 2 answers. Because regardless of what kind of number you plug in here, positive or negative, you would get a positive result. In this situation, x equals 0 is the only no-no. But in this situation, the x's must be positive. Remember, the condensing rules only work with positive numbers on the inside. But this is not condensed. this is an original if written this way. So that's the difference. If written this way, that would have been the answer. Written this way, negative 8's not allowed. So I just want that on your radar. Yes, ma'am? It wasn't squared originally, though. Originally, it was 2. Originally, it was a vertical stretch of a logarithm graph. And this logarithm graph would only exist to the right of its asymptotes. Now, if you assume x is positive, you're allowed to do that. So right there, the moment we did that, we allowed ourselves extraneous solutions to be possible. And then it did show one up. Here, the only number that x would never been allowed to be is 0. Here, x had better be greater than 0. This rule that goes from here to here assumes that the argument is positive. Okay? So I just want that on your radar. So check out example number 4. Bless you. You could either determine the domain at the beginning, or you could wait to the end to make sure your answers are allowed. To be real with you, I'm more of a fan of making sure, I'm more of a fan of waiting to the end and then going, was that answer allowed? Okay? But that's a personal preference. So you could either determine the domain now, which is x is greater than 0, because remember 4x had better be greater than 0. Or we can go ahead and solve for x and see what numbers we get. And if we only get positive numbers, we just look up and go, oh yeah, that positive number was allowed, and we're good. Okay? Completely up to you. What do we do first? Cancel the logarithm. She says switch it, and I think you mean convert to exponential form. Yeah. Let's cancel the logarithm. We can do that right now because that logarithm is alone. So I'm going to use an exponential base 2 to cancel this log base 2. On the left side, those things cancel and leave me with a 4x. On the right side, I have 2 to the 5th, which is 32. Divide both sides by 4, and you get x equals 8. 4 times 8 is a positive number. We're good here. All done. Number 5 is exactly like an IB test question that I give every year. Well, every year that I teach logarithms to my IB students, obviously. You cannot cancel a logarithm until it is alone. Thoughts? Dang? So let's just say we subtract one of these two to the other side. That's fine. Let's say we did that. You would have, let's assume you moved this one because it would have been easy. You'd have this alone, right? And you go, great, I'll cancel this log base 10 with an exponential base 10, won't I? But you see, but over here, you would have 2 plus log of x. And if you tried to raise that whole side, if you tried to say it was base 10, you would have to say 10 to the power of 2 plus log x, where 2 plus log x is the exponent. That leaves a logarithm in your exponent. So it doesn't cancel. So again, you do not want to cancel a logarithm until it's alone. How does one make it a singular logarithm? You can condense, and like Grayson said, you can multiply these two arguments. So because these two logarithms have the same base, I can condense these two logarithms to a single log. And then I'd have a single logarithm, which means I could cancel it. This is going to give me log of x times x plus 15 equals 2. Now, log is alone, and I can use a base 10 on both sides to cancel the log base 10. These two cancel out. I'm going to go ahead and multiply these two things. I'm going to distribute. I'm going to get x squared plus 15x equals 100. Don't fall into the trap of saying 20. It is 100. Oh, look, x squared, a quadratic. You cannot solve a quadratic unless it's set equal to 0. The good news for us is that the number in front of x squared is a 1. So this is one of the easy one to factors. One of the easy ones to factor. There we go. Where all you have to do is figure out what two numbers multiply to negative 100 that add to 15. 20 and negative 5 will do it. Leading us to our two values for x. That gives me x equals negative 20 and x equals positive 5. But only 5 is positive. Now hold on. For this question, x equals negative 20 is extraneous. But please listen, I don't want you to think that x equals negative 20 is extraneous simply because it was a negative answer. There are plenty of times where negative answers are allowed. Like I said, this original setup allows negative answers. The reason why x equals negative 20 is extraneous is because it violates the domain of one or both of my logarithms. So it's not just because we had a negative answer. No, negative answers are allowed. Answers that break the domain are not allowed. And this one breaks the domain because it makes a negative argument. I don't even care if it does it in both. The point is it allowed a negative argument, which is not okay. But this one, positive argument, 5 plus 15 is positive argument. This is our only true answer. How do you feel about condensing logarithms before solving for x? Not bad? Light work. Okay. Okay. Invariably, someone eventually asks, what if you can't get them to have the same base for the exponentials? Actually, you can't. Because 26 is not a power of anything. So what do we do? Well, we could say 8. We could say 8 is 2 to the third if you wanted to, but I don't see a reason to. Because we have enough knowledge now to see that it doesn't matter what we do, we will never get that to the same exponential base as that. What that means is you might as well just go ahead and cancel the 8 now. So how do I cancel exponential base 8? Log base 8. Yeah. Oh, you know what I need to do? Hold on. I need to put the video on pause just for a quick second because I'm going to find something on my phone and I want to put on the screen. I want it on the video. Okay, I found the text message that I wanted you guys to see on this video. Former student of mine named Thomas Deneen, went by TJ. This is work from him in college. Okay? Look what kind of work he's doing. What do you mean you can't see it? Poor quality. You guys crapping on his handwriting. Logarithms. Okay? He says, working on logs, and I still hear in my head every time, class, how do we cancel log base 10? And the answer is exponential base 10. Yes, he has my number. No, I just gave it to him. He's a good kid. He was my student twice. He was my wife's student for 3 years because he was a young Marine. He's not a kid anymore. He's a good man. But my point is, he remembers the way that I teach this, and it still makes a difference. Okay? So I just said, how do I cancel exponential base 8? And you would all shout out, log base 8. Cool beans. So we're going to use log base 8 of both sides. I don't really have the room to squeeze that in here. Just know that I put a log base 8 on this side and a log base 8 on that side. When I do that, it gets me x minus 3 equals log base 8 of 26. So you get x alone by adding 3. So the answer is log base 8 of 26. Oh, plus 3. No, whatever the heck that is. You're welcome to type it on a calculator if you'd like to. This is the exact answer. That is the exact answer. Now, clearly, I couldn't have you type that. But it could have been, this question could have been on a no calculator test. And the answer is log base 8 of 26 plus 3. That's the answer. I mean, what does that answer equal to? Well, I know 8 to the first is 8, and 8 to the second is 64. So this number is between 1 and 2, plus 3. So the answer is between 4 and 5. It's between 4 and 5 somewhere. I'd imagine it's close to like 4.2-ish, if I had to guess. That's a total guess, though. Look at this. This is meant to scare the crap out of you. It just is. Yes. Okay, so hold on. Hold on. Shh. Calm yourselves. We have two different exponential bases here. And unfortunately, they both have an x in the exponent. E and pi are both numbers. So what do we do? Okay, I heard someone say natural log. Now the reason why they said natural log is because they were trying to cancel this e and that would isolate this x, right? But what in the world is the ln of pi to the 1 plus x? Remember, your job is to isolate x. And if you say the natural log of both sides, you now have an x inside a logarithm and an x outside of a logarithm. And that is no bueno. We don't want to do that. Is it possible? It is still possible, but you've made the question more difficult, believe it or not, by using the natural log. Here's what you should do every single time you have x's in both exponents and you cannot get a matching base. Do yourself a big favor and just use the common log of both sides. Just use log base 10 of both sides. And I will show you why in just a moment. Let me figure out what color. I'm going to write in green this time. We're going to write log of e to the x equals log of pi to the 1 plus x. And why is that beneficial to do? Well, the log bases are equal, yes, but...
Oh, you can subtract that one and condense it? And make it like
you could... Okay, you're not wrong. You could do that, Ahmed. You could. But if you did that, I think that you'd be creating a little bit more algebraic steps to solve. It's not wrong, and yes, it would work. What Ahmed said was we could bring both logs to one side and condense. And since it would be subtraction, and when we condensed, we'd have a fraction inside our logarithm. He's not wrong. That would also work. But I feel like it's a little bit more work than I want you to do. But yes, it would get you to an answer. So good. Always trying things. Trying anything to see what it does for you. But that's not how I would have done it. But yes, that works. Here's how I would have done it. The reason why we like to use the common log is because it would allow us to get those x's out of the exponent position. Getting us to this, x log of e, whatever log of e is, equals, make sure you have this in parentheses, 1 plus x log of pi. Because remember, pi is a number, so log of pi is a number. And log of e is a number. It's almost like it could have said 5x equals 1 plus x times 3. And if that was the problem, if that was an algebra question, if this said 5x, and over here you had 1 plus x and a 3 on the outside of the parentheses, what would you have done? got quiet on me. Excuse me. Sorry, I just hit puberty recently, apparently. Let's write out. What if I had written this for you? And I told you your job was to solve for x. What would you have done? What divide? What in the world are we all smoking? This is an Algebra 1 question, and not one of you... Chayla, save me. Distribute. You don't want to divide by 5 because you still have an x inside there. You need to distribute. And net, okay, so you're all cool with the idea that when there's a number outside the parentheses, you can distribute it, right? Guess what? Log of pi is a number. So distribute the log of pi. I don't know what log of pi is, but you distribute it like this, and you get log of pi plus x log of pi. Back to the Algebra 1 example I just showed you. How would you have gone forward from here? Subtract 2x. Oh, you would have brought everything with an x to one side. And things that didn't have an x to the other side. Oh, yeah, I'm going to bring this that way. I kind of wrote big for this little box, didn't I? I'm going to subtract x log pi to the left side. It's going to get me this. X log e minus x log pi equals log of pi. Divide what? Wait, substitute. Wait, hold on a second. Your job is to get x alone. There it is. Who said that F word? Hannah did. Hannah did, that nerd. She said factor out x. Good job. One of my favorite F words. Not my absolute favorite F word. One of my favorites, though. My favorite F word? Fun. Okay, so what we're going to do is we're going to factor out x as a GCF. And now, to get x alone, now you get to divide. So is the answer pretty? No. And I'm out of space, so I'd say I'm going to put the answer over here because I found some space right here. Sorry about that. But look what x is going to be. X equals log of pi over log of e minus log of pi. Hold on. Stop. There is no reason to do more with this answer other than we can. So because I can do more with it, I want to do more with it. This answer is perfect. There is no reason to go further unless the directions required the answer to be written as a single logarithm. Because this can be written as a single logarithm. Down here, you can condense. So let's condense on the bottom. And again, I'm even gonna change colors because we don't have to go any further. But I'm a nerd and I want to see it go further. That is, oh crap, my fraction's upside down. Man, yes, it should have said e over pi. Womp, womp, womp. All right, let me just do this. Sorry, guys. There. And last but not least, remember what I said? I want to be able to write this as a single logarithm. So use change of base. Log base e over pi of pi. There is the answer written as a single logarithm. I have no clue what that equals. Now let's not find out. I don't want to find out. because I used change of base. I'm undoing change of base. Remember change of base says log of argument over log of base? And it still feels like I should be able to use the natural log, and I could. I could keep working this thing if I wanted to and make it a natural log, but there's no reason to. Isn't that special? Again, I feel like... Okay, negative 7.909. Thank you for that. This in green is a perfect answer. This is if the directions specifically said write the answer as a single logarithm. There is no reason to do that unless you're told to. I'm just letting you know, okay? You know what else you could do to solve logarithms? I mean, you could do them by hand. Look, they didn't have to have the same base. Solve exponentials. They didn't need the same base. Common log and change of base will always get you there. Or you could just use technology. Solving by graphing, and this thing is like, oh look, you could solve by table and estimate that way. I mean, I think that's stupid, to be honest with you. I mean, if it was me, I'd just do second trace intersect and I'd get an exact answer instantly. But I don't want to take away from the skill sets that are being taught. Okay? So because here's the thing. You have a graphing calculator that allows you to solve with second trace intersect. But how did they do this before we had graphing technology? The answer is, no, they did. They used things called logarithm tables. They're like trig tables. They were lists of decimals. And how were the decimals calculated? They were calculated by hand using a process called successive approximations, which is horrific, okay? We are not going to do that. But I do want you to understand how human beings did it. Oh, you know what? We're going to call the we're going to do it here and call the video. Let me show you what they want you to do. How was pi discovered? That's a completely different video. Happy to tell you, but let's do this first. It says solve 2 to the 3x equals 9. So obviously I'm going to go to y equals, and so 2 to the 3x and what? 9. Now let's talk about this, okay? Here's what we know. 9 is not a power of 2, correct? 9 is not a power of 2. You know what is a power of 2? 8. 2 to the third power is 8. So if x was 1, this function equals 8, which is almost 9. But if x is 2, this gives me 2 to the 6th, which is a big, big number. That's 64. Much farther away from 9 than I want to be. But you know what that tells me? That tells me my answer is between 1 and 2. And that is the beginning of successive approximations. Okay? So let's go to our table. And what we see is at x equals 1, my answers were similar, but not perfect. At x equals 2, oh boy, we've gone way too far, haven't we? But we know the answer's between 1 and 2, so it's bigger than 1. So go second, table set. Tell your table to start at 1 and tell it to go by 0.1. 0.1. This way it goes 1.1, 1.2, 1.3, okay? This is how successive approximations works. And by the way, you could do this by hand. We're not. We're asking the calculator, but this is the process. So you go back to the table, and we see, here y1 was less than 9. Here y1 was more than 9. That means the answer's between 1 and 1.1. So we go back to table set, and we tell it to go by 0.01. This is how successive approximation works. And now you go back. And you start narrowing it down. Still less, still less, still less, still less, still less, went over. Poop. We know our answer is between 1.05 and 1.06. Second table set. 1.05. Go by 0.001s. It's painful, isn't it? Aren't you glad that you don't have to do this? Yeah, second trace intersect is thebomb.com. Yes. Now look at what's happening. Less, 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 less. Wow. Okay. We now have the answer out to 3 decimals. It's between 1.056 and 1.057. Could we continue this process? Yes, we could. We definitely could. Well, and people did this by hand back in the day. But this is how you could approximate answers using the table. My point is, if you ever saw a no calculator question that simply said, someone's at the door, yeah. Let's say it asked you to talk about where the answer is and how you know it. That's how you would have done it, okay? Now, clearly, we would just use second trace intersect to find the exact answer, because even that's not exact. The exact answer is 1/3 log base 2 of 9. That's the exact answer, 1/3 log base 2 of 9. But we could do it like that. Okay. Thank you so much to Hannah for the new art, and thank you so much to all of my nerds for playing with me today. It's been a blast.